Ladies and gentlemen, the following speech will be delivered by Professor Gabriel Herl of Technische Hochschule Deggendorf. Mr. Herl will deliver a speech titled RoboCT at Deggendorf, Current Advances in Robotic CT, exploring recent advancements including workflows for easy scan planning and precise calibration techniques. Professor Herl is a renewed researcher who specializes in the robotic CT trajectory optimization and calibration. Professor Herl, if you are here, you are here. The audience is eagerly waiting for your lecture. You can use this mic or this. Okay.
Can I use a mouse too?
Yes.
Yeah, hello. It's very great to be here. Thank you very much. Thank you for the nice introduction. And mostly thank you, Josef, for inviting me and for this great event. It's an honor. Okay, so we're in Deggendorf Institute of Technology. And this is our system. For the people who don't know where Deggendorf is, it's in the south of Bavaria. We're currently 10 researchers. There's another professor, Simon Zabler. He sadly couldn't be here, but Anton Weiss is here for more technical details, if there are questions. A lot of stuff is happening right now. Currently, we published a review paper. It's about 60 pages long, so there's a lot in there, but it's not peer-reviewed yet. A lot of stuff happening right now. So let's start. Let's start with let's start here. Great. Okay. So let's see our system in action. Here we have two robots. They're both on linear axis, and in between there's a tailgate of BMW, and we're doing a 2D scan of a projection. It's real time. We can see here it's 17.8. On the left side we see, bottom side, the digital twin, and the digital twin we do the planning, and on the right bottom side we see the current projection. So this is live. We do the planning in the digital twin, then it just happens. And now we can see this is a 2D scan. And yeah, this is made by Anton Weiss, one of the PhD students, and he's here. So let's quicken it, let's make it a little bit faster. We can see the system is working, the detector is doing all the work, it's moving, and the source is more or less stable. Sometimes some time goes on here, then there was an reorientation, and then after about, we can look at the clock, after about 5 or 6 minutes, the thing is more or less completely finished, and we have a big projection of the complete thing. So if we have a thing here, we can place it inside, be a little bit careful that we don't crash, so we have to do the stuff in the digital twin, and then go 5 minutes, and we have a big projection. This projection took about 5 minutes, 350 megabytes, so it's a lot of data. And then, yeah, a lot of pixels, so this is 15K to 11 or 12K pixels, so it can be a lot of data. Or another example here, 2D scan of a bike, but obviously we can do more than 2D scans. So for example, in this case, we can do a region of interest scan, focus on a part in the frame of the car, and here, if we zoom in, we can see a crack. So there has been a crack. We can look at, as an example, bikes and look for small details in 3D. Or another example, here we look at a wind energy rotor blade, only the tip. On the one hand, we can do a 2D projection, and then obviously we can do 3D reconstruction, 3D CT, and here are the examples. Here we can see different slices through the volume. It's a little bit small, but we can see cracks, we can see pores, so we can do the 3D quality testing. So we can do 2D scans, we can do 3D scans, can do it precisely, but what are the current challenges? What do we think is really cool stuff happening today? So I will go quickly through 4 topics. One, we want to speed up RoboCT by fast flybys. One, we want to make it more usable by automatically planning trajectories that optimize the image quality. By improving the accuracy, obviously calibration is a big topic. and then by mobility, by bringing the RoboCT out of the lab. Obviously, Red Analytica is a step farther in this topic, so yeah, we're looking for cooperation here. Okay, so let's start with speed. And one of the things we're doing right now is flyby scans. What does it mean? It means that the RoboCT doesn't have to stop when it takes a picture. So it does a continuous movement. And this continuous movement, it takes pictures in 49, and then it starts. And when it starts, it just continuously makes images. And what it does here is something like a sinusoidal trajectory around this object, around this test object. On the left bottom side, again, we see the digital twin. On the right bottom side, we see the current trajectory in real time. And again, it's like 10 minutes before 18 o'clock. And if I speed it up a little bit, let's wait a little bit. If I speed it up a little bit, not that easy. And we can see that it makes something like a sinusoidal curve. To do it smoothly here. Yeah, here it's fine. So it does something like this. And this is planned in advance, just with a Python script mostly. And yeah. And this is finished in about 5 minutes. To be honest, with 5 minutes, the quality wasn't perfect. So hey, we repeated it in 20 minutes, but this is real time. And then the reconstruction result can be seen here. So this is a flyby scan of 20 minutes. It's a 1.5K voxel volume, voxel size of 139 micrometers. It was reconstructed with a standard reconstruction algorithm. And we can see here, we can even see the layers in the 3D printed material. So yeah, even with flyby and very quick, fast scans, we can do 3D reconstruction. So obviously we want to improve here. This is the current work. But RoboCT does not mean that we take long. We can be fast. Okay. Next is usability. We want to do automatic testing even in complex scenarios. And here we have a cooperation with BMW. It's Jonas Schnitzer is one of my PhD students. And he planned an automatic trajectory, and he has algorithms to do this inside of different regions of car bodies. And we can see here this is not real time, but this is an automatically planned trajectory. And we can be sure that the robots do not crash with the car body, even in these complicated situations. Yeah, and he uses this for checking defects in car bodies. The main topic here is reachability, don't crash, and find the projection views that optimize image quality. And this here uses prior knowledge, so I have to know what kind of car body is placed in the system in which place. Okay. Results here can, for example, look like this. I hope you can see it. Here on the left side, we can see a rivet, for example. In the middle, we can see a faulty adhesive bond. There's some adhesive lacking. On the bottom side, on the bottom, we see some screws. This is reconstructed with Voxray. One of Voxray people is here too, because sometimes calibration can be a little bit difficult. And in this case, we can use Voxray, and then the reconstruction nevertheless does work pretty well. So, yeah, some real images. Let's go on. Next, like I told you before, the thing with the car body, we needed the prior knowledge. Right now, we want to do it live, without any information about it. We just start scanning at some place, and then want to see, hey, can the RoboCT for itself look good? What's a good path? And we do it with reinforcement learning. And at the start, we have a training phase. This means that we load different kind of objects from a database into the training framework, and then we start with different agents, and they try out different routes, and then we give reinforcement to some of the routes. And after a certain phase, we can say, hey, it finds this thing. So it rewards if we avoid big attenuation length, and it tries to find complete circular trajectories. And after some time, we can take the trajectory, put it in the digital twin, and start scanning. Look, for example, like this, and then automatic planning. here done by Simon Whittle, one of the other PhD students, and then it starts. So here we're not completely finished. We have to look more at the results, optimize it a little bit, but in practical we can just place an object there and start scanning. So press a button. Okay, then I mentioned calibration. Sometimes calibration can be difficult. If we look at the left picture, it's a little bit on purpose that our robots do some wrong moves. But the position accuracy isn't that high for a lot of robots. So if you don't calibrate, you get the signals on the left. If you do calibration processes, you get the image on the right. This is an image of a Lego car. On the left, with the really strange artifacts. On the right, we see clear edges. You can even see defects in the car. But this requires a second scan. So if you want to have perfect geometry, we do need a second scan. However, we do have algorithms and work on algorithms to do it without a second scan, obviously. Yeah. And this is, for example, this here. Here we're looking at a bicycle helmet, and we want to scan without a repetition. We want to do a scan in which the robots could be extremely wrong. We could look at a mobile case or maybe a system that is only able to do 2D stuff without good positioning. And then we place markers at the object. We just put them there. And then in the projection images, we can see these markers, find them. And from the different 2D projections, we can estimate where are these markers. And then in an iterative process, correct the positions of our 2D projections. Next thing is we want to do mobility. And one of the projects that we get funded right now is that we do 3D CT scans on bridges. So this is a little bit crazy, I have to admit it, but we can use a Betatron of BAM. It has 2.5 MeV, and here we want to try, hey, what can we check in bridges? So we're looking for different defects, and yeah, let's see what happens. And obviously, calibration will be a big part of this project because we have to bring the stuff there. Everything can be shaky. Yeah. A lot of other projects are planned right now. I'm looking very much forward to a project with Radalytica. We are currently planning optimizing RoboCT for aerospace. For example, we have a Eurostar project here. And another project that I'm looking forward is using drones for 3D CT. So if we say, hey, we can do it with extremely shaky manipulators, so why not use drones? And the goal here is to do this to check wind energy plants. And here we have a current project here in hope that we get funded and other stuff too. Okay. Then I talked a lot about, hey, what are the challenges, what can we do right now? But hey, mostly we can do CT for large objects. We can do it with arbitrary trajectories, we can do laminography and tomosynthesis, we can do helix, we can use circles, limited data, or just arbitrarily placed positions that are optimal for a use case. We can make 2D projections, we can do 3D scans. And if you're interested and if you have objects and you would like to have scans, come to us. Accuracy is about 100 micrometers. Price, obviously, is it an easy use case or is it a complex, big thing? And yeah, we would like to find more people who want to do scans. And yeah, I think I was relatively quick. Thank you very much again. Contact us if you're interested in scans or just some research. Enjoy your time, and again, thanks a lot for being here. And yeah, thank you.
Thank you very much, Professor Herl, for your insightful presentation. Now there is the floor open for your questions. Please raise your hand correctly and wait for the microphone before you start speaking.
Yeah, thank you for the interesting presentation. You mentioned in this one sentence you want to check drones.
Yes.
I'm a little bit wondering, you have to handle heavy weights, maybe, and you have to handle radiation protection.
Radiation protection with wind energy plants is no problem at all because there are no people near this thing. So
where do you plan that? In companies and oil plants and?
yeah, the idea is really to use it on real wind energy systems. And if you're high in the air or maybe over the ocean, then there are no human beings. So if you just do a little circle and say no people are allowed here, that's no problem. I find it a little bit scary, but right now, in this bridge project, we have a guy, Sebastian Schulze from Bauray, and he's allowed to scan on bridges, even if there are cars driving on the bridge, as long as they're driving fast enough.
Passagelos, yeah.
So this radiation project is not a problem at all. Obviously, finding the right drone and finding X-ray equipment that's light enough and still can penetrate enough material is a little bit difficult. But I think that's possible. It will not be possible for every region of the wind energy plant, but in some regions. That's the goal of the project.
Can I ask a second question? If you have to calibrate your robots,
sure.
Many people do optical calibration. Do you also combine that optical and X-ray calibration? We did test a lot of stuff. We did compare a lot of stuff. Here, Anton is a guy that did this. The best result were when we did a second calibration scan. We did scans with laser trackers, for example. Can be done. It was the most easy and cheap way. I don't know. Do you want to add something? Sure.
So you can actually calibrate the whole system as a unit for both of the robots, classical robotic calibration using also X-ray data from a calibration object and afterwards applied to the scans. You lose spatial resolution, but you still can do about 150 to 180 microns without a secondary calibration scan afterwards for several weeks until you have to do it again.
Are there any more questions? I see a hand raised.
Thank you, Gabriel, for the nice overview on your assets. I just wondered about the calibration of that helmet. Is that relying on the accuracy of an external optical metrology system to pin the markers, or is it intrinsic?
It's an iterative process. So it first finds the blobs inside the projections, and then that it tries to find which blob in which projection corresponds to which other blobs in other projections, and then it tries to find which position is it probably in 3D space, and then it does an iterative optimization, and yeah, it works really well. Paper will be there soon, and then we have to obviously test how much markers do we need, how much do they need to be in different regions, for example. Obviously, if there's a massive object, we can't place markers inside the object, so there are still problems. But if we have the possibility to put enough markers on it, and we can see the markers, then we can do the calibration. For example, for a bridge, that will be difficult, because, hey, the question is, can we read the markers good enough, and can we place the markers on the right spaces, the right spots? So, yeah. But in theory, we can do, for example, 2D, if there's just a system that normally only can do 2D projections, then we can do 3D reconstruction using this technique.
Okay, cool. Thank you.
Thanks.
Thank you for the wonderful talk. My question was, what about the X-ray source? What is the current KVs that you're using, or what is planned in the future?
We're using 225 kV. We could use more, and we could use other sources. It's more or less a money question. At first, when we started doing this, we didn't expect that we will be able to do precise 3D reconstruction anyway, because we thought robots and everything's difficult. Right now, we would like to have a source with a smaller focus spot. Right now, we are about 150 micrometers. That's possible to scan. Or up to 100 micrometers. But yet, all depends on which kind of use case and which kind of source is ideal for this case. Yeah. But we're doing it with a Betatron 2, and the Betatron has a lot more power, but a lot bigger focus spot, so this is always the question, what do we aim for?
Very nice talk, and
Thank you.
yeah, I love the system you've put together there. It's really nice. A couple questions. The first is anyone, are you working on this, or do you know if anyone's able to, let's say, extract a point cloud from your structures that you scan?
Of course, sure.
And so can you do dimensional comparisons with the models, for example?
Yes, we did that. We did publish papers and compared different methods and
Using the same X-ray technology, you're not adding a different scanner system in place?
No. We can do metrology with this. Obviously, it's not as good as an optimized machine for metrology, but right now the biggest problems are the size of our focus spot. We're not limited due to the calibration processes.
Actually, just a suggestion, mind, but I was at a conference 2 weeks ago where somebody was presenting scans of mummies and bog bodies around the world. Actually, very cool presentation. I liked it very much. And they had a serious problem to actually put Ötzi in a standard CT gantry scanner, because this guy actually is twisting his arms like a Nazi style. So the thing is, actually, they were wondering how to get like a good scan of this thing. Maybe you want to.
If you have context of the people who have
sure.
Ötzi and they can scan Ötzi, obviously, I would love to.
Might be a nice paper.
Sure.
Thank you very much for your questions. Don't hesitate, please. We are on time, so you can ask your questions next 10 minutes.
Way too fast, I'm sorry.
Hi, thank you for the presentation. About the robot, is there any possibility of electronic damage on the robot? Because you're moving them while scanning, so they're under radiation. Is there any possibility of electronic damage?
In theory, there can be damages on the electronics, on certain sensors, for example, or that's why sometimes you have to be a little bit clever. Don't always have the rays on the same, or don't put certain sensors inside of the main beam, but we haven't heard about any problems with the robots. More like if there are extra sensors or anything, then there can be damages, but it's not a big problem.
Yes, so you do not have any shielding on the robot,
As far as I know, there's no extra shielding for the robots, no.
Okay, thank you.
Well, if there are no more questions, I have to thank you, Professor, for your nice and interesting talk.